Hello everyone. Today we're going to talk about close hashing, and this time we're going to do some analysis on close hashing. So let's say that we have n number that's already inserted in our hash table. And also m is the table size. So we can define the load factor, the parameter alpha, as the n divided by m. So it means that what's going to be the percentage of like the number of items that we have to the total items that we can insert in the hash table. So let's say that let's assume that the probability of finding finding a home for any new item that we insert are all equal to each other. So it means that also the probability of having some collision in this table that we have with this load factor alpha will be equal to n divided by m. So n divided by m is the probability of a collision for like one new item. And now assuming that we're going to see that if there's another collision or not. So for the second times collision, okay, when we are going to insert a new key, okay, we have now n minus 1 item in the table. Okay, we know that one of the item is already occupied, so we have n minus 1 item, and also the tables the table size, now we know that 1 is occupied, is going to be n minus 1. So the probability of having two collision is equal to this expression here, that is n multiplied by n minus 1 divided by m multiplied by m minus 1. So we can generalize this formula for finding that what's going to be the probability of having I collision in inserting a new key. That is going to be n multiplied by n minus 1 n minus I plus I divided by m minus 1 and m minus I plus 1. So that is the probability of having I collision, okay, I in the hash table that we have. So if we can approximate this value that we have here. So suppose that n and m, okay, n and m are very large numbers, okay, so n and m are very large numbers, then we can approximate this expression as, let's write it here, n divided by m to the power I. Now we can find out what's going to be the expected number of probes, okay, for having like I collision when we're like to have a successful search to insert a new key. That is going to be 1. Sorry about that. It's going to be 1 plus the sigma of I equal to 1 to infinity. Okay, and I is, as we said, that is the number of collision that we have, and infinity goes says that if we have like a very large number of collision, so that's going to be the expected number of the collision. So n divided by m to the power I, that we said that's going to be like the value for the collision that we calculated above. And if we just calculate this value, this is equal to 1 divided by 1 minus n by m. And as we learned before, n divided by m is defined as alpha. Okay, so we can write this one equal to 1 divided by 1 minus alpha. So now the cost for a successful search, okay, regardless of when I insert or we're going to delete, okay, it's the average gonna be the average cost when we already inserted. Let's say that we inserted n minus 1 keys before. Okay, now having this number of like the cost or the like the number of probes for each node that is equal to this one, and now we're going to see what's going to be the average. So we need to see that what is this what is going to be this value of alpha that we had before for every other items that we inserted before. So because as we said, this alpha is the number of items that we have for now, okay, divided by m. Okay, so if we want to see that what's going to be the average cost, okay, we need to see that what has been the previous alpha and sum all these values for like all previous of value of the alpha to find the average case. So this means that we need to, for getting the average, we need to have this 1 divided by alpha that stays for the average, and having the integral of from 0 to alpha of 1 divided minus x of dx, that is equal to 1 divided by alpha, the natural logarithm of 1 divided by 1 minus alpha. And as we said, okay, because this alpha that we have here is the current alpha, but for when we are inserting or searching for a value, let's say that for the nth the item n that we inserted. But before that, we need to see that what has been the cost or the number of probes that we have done so far for all other items. So the average, this all gives us the average that is equal to 1 divided by alpha, natural logarithm of 1 divided by 1 minus alpha. We should keep in mind that the cost that we calculated here is a lower band on the cost, okay? So because we had some assumption that the prob sequence is based on some random permutation of the slots, okay? And we have all the slots have the same like the probability for being to having some new items, okay? But as we said that like the distribution of data that we are going to insert, okay, might impact this assumption. So that's, as we said, this is just one lower band, and the actual one will be higher than this amount.